To continue on with periodic trends, next we're going to look at electron affinity. Affinity is essentially a want or desire, to bring something in or to get something. So electron affinity is how much an atom wants an electron. Now, the way that we measure this is by the amount of energy that's released when an electron is added to an atom. We can kind of think of energy as the sort of the currency, I guess, of this transaction, sort of. So we give an atom an electron, and it pays us for that electron based on how much it values having that electron. Now, of course, this is it's an analogy, so don't take it for fact or something, but it might help you kind of wrap your brain around it. So electron affinity is essentially how we measure how much energy is released as we add electrons to an atom. So that means we are turning our atom into an anion. Some people like to think of electron affinity as kind of the opposite of ionization energy. Rather than seeing how much energy we have to put in to get an atom to release an electron, this is how much energy do we get back from the atom when we add in an electron to that atom. We still measure this in terms of energy per amount, kilojoules per mole. All right, and to give some baseline examples, radium has an electron affinity of about 47 kilojoules per mole, whereas chlorine, up in the upper right of the periodic table, has an electron affinity of about 349 kilojoules per mole. So let's see what that would be like, 7 times as much as radium, which is pretty crazy. So electron affinity has a trend, just like all these other things, and it increases as we move up and right on the periodic table. So first of all, why up? Well, since our atom gets smaller as we are closer to the top right of the periodic table, those valence electrons are closer to the nucleus. So that means where our valence electrons are at, that's a stronger attraction. Now, if we are adding in an electron to this atom, it's going to be in that valence energy level. So small atom getting an electron in close to the nucleus is going to be pulled in very tightly, very strongly by that nucleus. Okay? What we get is therefore a much more stable atom. We have things kind of playing by the laws of physics. If it feels a strong attraction, it's going to move into the atom, pulls it in. We end up with a lot of energy, therefore, released from that atom as it gains in electrons. So if we have an atom with a stronger attraction, it's going to be more willing to take an electron in, and it shows that by the amount of energy kind of released. It becomes much more stable than a big, bulky atom that cannot have such a strong attraction to those electrons, and would therefore just kind of give a little bit of energy back out as a result. So atoms farther up on the periodic table end up taking in electrons because they have such a strong attraction, and we see that strong attraction from a release of a lot of energy. Why right? Well, atomic radius still kind of plays a part, but if you want to take it from another angle, you can also think of how things make ions and how they tend to gain or lose electrons. Over on the left side of the periodic table, we have stuff trying to lose electrons to kind of get back to a previous noble gas's electron configuration to become stable. Well, if we're looking at how much energy is released as things become more stable, and these guys on the left side of the periodic table are trying to lose electrons, forcing them to gain an electron is not going to be all that useful to them. So they're not going to give a lot of energy back out. It's going to be like just not a good time. On the right side of the periodic table, we have the opposite. We have atoms that want to gain an electron to get to that octet, to get that noble gas electron configuration. Okay, so giving something an electron on the right side of the periodic table tends to make things more stable anyway. It's kind of like what they're shooting for. So there's a bigger payout in energy. We give an electron, it's like, oh yeah, I was looking for this. Boom. Sends out a lot of energy as a result. Much more stable. Okay, so we get a higher electron affinity over on the right side of the periodic table because those are the things that are looking to gain an electron anyway. So when we give one of those atoms an electron, it's like, oh, nice, sweet, and it pays us back with a lot of energy to show that it has become a lot more stable. Okay, bigger loss of energy shows something is becoming much more stable from a high energy state to a lower energy state. Okay, so that's electron affinity. Then electronegativity is a little bit odd, and it will hopefully make some more sense when we get into stuff bonding, because it really can't be measured without getting stuff to bond together. Electronegativity is essentially about how tightly atoms hold on to their own electrons, specifically when they get into kind of a situation where they must share electrons with something else. So when we talked about the covalent radius, where we have atoms kind of overlapping their electron clouds like this, okay, that's a case where atoms are sharing electrons, okay, and that's a bond. We'll get more into that later. But for now, all you need to know is sometimes atoms need to share electrons, but that doesn't mean they're going to share them fairly or share them evenly. Sometimes atoms are a hog for electrons. They're going to try and keep it all to themselves. Okay, so you can think of electronegativity as a greediness kind of ranking system. I say ranking system because this isn't measured. Electronegativity is not something we can, we hook up a meter to it, or we test something out and say, I got the numbers. Instead, we look at how things form bonds with other things and where the electrons go, and then we base it kind of on that. We rank them. We say, well, this is going to be a little bit more greedy than this one. This one's a little bit less greedy, and then this one. And then that's kind of how we form this sort of list. So we do still have a number that we assign, but it doesn't really mean something as quantitative as an actual measurement. There's no units for this. This is not measured in energy like electron affinity or ionization energy. It's not measured in length or mass or anything like that. It is just a number to represent how greedy an electron is, or an atom is to its electrons. So our elements are ranked on a kind of a weird scale. It's from 0.7 to 4. Up at the at the bottom of the scale, we have francium. Francium's down on the bottom left of the periodic table and has an electronegativity of 0.7, basically about as low as you can go. Whereas fluorine in the top right of the periodic table has an electronegativity of 4.0. Now, if you see the trend from there, that the biggest electronegativities are up in the top right, you might say, oh, well, then helium should have the biggest electronegativity. So why is fluorine at the top of the scale with 4? Well, we don't count some things. Some stuff in column 18 in row 7 are not ranked because of how we define this. Since electronegativity is about how things share electrons across bonds, we need things to be able to bond to put them in that ranking. A lot of elements in column 18, those noble gases, are stable as they are. They already have an octet. They already have 8 valence electrons. And so they don't really need to form bonds to become more stable. So most of those elements can't be kind of compared to each other as which one's going to be greedier with their electrons and which one's going to be more fair or more loose and loosey-goosey with their electrons, because we don't get the chance to observe that. So we kind of just ignore column 18 and because they don't really fit that definition. Same goes for some of the elements in row 7, especially kind of the elements that we're still working on discovering. Essentially, these are synthesized by bashing particles together and getting them to show up for a fraction of a second. So we don't really have the time to get them to bond to something else and see how they share electrons. We barely get them to show up in the first place. It lasts so very long a time. And then they just break apart into other little more stable fragments. So these synthesized elements are a little bit tougher to kind of keep isolated and study because they break down so quickly. So as a result, we can't really rank them either. So our list is a little bit more limited. Okay, but why do we get this trend? Why do we end up with electronegativities highest in the top right? Why are our elements in the top right of the periodic table more greedy with their electrons, and why are the things down the bottom left a little bit more willing to share? Well, if we follow what ionization energy and electron affinity has told us, ionization energy is essentially how hard it is to make a cation, and electron affinity is how stabilizing it is to make an anion. And both of those are highest up in the top right. So in short, the stuff in the top right of the periodic table wants to gain an electron and is good at gaining electrons, not losing electrons. Stuff down the bottom left is the opposite. Okay, they're very good at losing electrons, not so much at gaining electrons. So we end up with elements in the top right not so willing to give away their electrons. They want more electrons, not less. So they're not going to want to share their electrons. Okay. I think I have this flipped wrong. Ooh, ignore this for a second. Let's see, therefore, oh, I see. Never mind. This is worded kind of weirdly. So elements on the far right and far top are going to be less willing to give away or share their electrons, which giving away their electrons and sharing their electrons would go along with a lower electronegativity value. Instead, they would rather take in or hoard their electrons, which would mean a higher electronegativity value. I got mixed up on the sentence structure there for a second. It's not written very well by me. That's unless you go back and edit at some point. So we can kind of break this down by some of the other periodic trends. We can show how atomic radius plays into this and things like that. But for the most part, we can get the idea just by looking at the other periodic trends.